In this video, we're going to introduce three types of bonding that we're going to discuss this class. What is bonding? Bonding is what holds atoms together. So this is how you get water to form from hydrogen and oxygen. This is how you get sodium chloride to form from sodium and chlorine. Bonds are what holds elements to other elements. To start with, ionic bonding. What is ionic bonding? It is a charge attraction between ions. So when I have a sodium plus and a Cl minus, there's a big positive and there's a big negative, and they're attracted to each other. So they move in, they pull up, they stick together. These are extremely strong attractions. They are full positives and negatives. They are permanently there. They can be attracted to each other, and they just stay constantly drawing towards each other. Effects of this are that ionic bondings tend to be fairly high melting and boiling. The vast majority of ionics are solids at room temperature because they have so much attractive force they can't really freely roll around like a liquid would want them to. Many of them also tend to be fairly low at conducting. They don't conduct electricity well. If an electron comes in, it just gets caught by the sodium, or it gets repelled by the chloride. So flowing electrons through ionics isn't usually the easiest thing. They also tend to be reasonably brittle. If we think about a crystal of sodium chloride, it is just continuously piling more sodiums and more chlorides on. A bigger chunk of salt is just more sodiums and chlorides connected in series. This, however, makes them quite brittle. If you were to hit this material, so hammer comes down, slams right here. The net result is that it's going to take this section and it's going to push it down. If it hits enough to actually push it, now I've got positives near each other. These are going to repel. And I've got negatives near each other. Those are going to repel. That effect is I displaced it a little bit, and now the material wants to push itself apart. This is why ionic crystals tend to shatter. Rocks, when you break them, they don't chip a little bit, they don't slightly deform, they break, they chunk off. As soon as you create a little bit of a slide between the ions, all of the ions push each other apart and it just runs down the material. And so they tend to be fairly brittle. They can be tough. They can take a lot of power to do it, but when they break, they tend to shatter. Well, ionic bonding is about holding molecules together with charge. This is a bit different than metallic bonding. Metallic bonding is still some charges, but they're not ions. I have my nucleus, a bunch of nuclei, and I have my electrons. And the orbitals for metals, we'll just draw them as giant spheres. They're really usually d orbitals for our transition metals and the like, but you can have a sodium metal or something like that, where your outside edge is just s orbitals. And there's electrons. Metal orbitals are large and diffuse, and they reach out in space enough that they overlap with each other quite well. As a result, the electrons kind of spend time in the orbital space of other electrons around other nuclei. These electrons are not rigidly held onto one atom. But the negative charges do mean that the protons are attracted to it. And so those protons end up holding on to a bunch of electrons around them, and it keeps the metal together. These electrons are called a sea of electrons. They're more or less free-floating. They can move around. If an outside electron comes in, it can just push the next electron over, push the next one over, push the next one over. It can just bump them all along the line. The net effect is I can put an electron in on one side and have it come out the other. Metals are very conductive. because those electrons are free to shift and flow from one nuclei to the next, it makes it very easy to move electrons through the material. So metals are very conductive. Additionally, well, if all you have is a bunch of circles that need to overlap, if you were to hit and force some of these down, unlike the ionic material where they'd now be a bad lineup, these still just have electrons that can be shared. And so if you hit a metal with a hammer, it bends, it deforms, it reshapes, but it doesn't shatter, at least not most of the time, especially not if you make it a little bit hotter. This is how blacksmiths work iron or any other metal. Because the metals just kind of need to be in contact so their electrons can freely flow to each other, pushing some of the atoms out of the way doesn't break them apart. As a result, these are very ductile or malleable. We can extrude these, you can heat up metal a little bit and then force it through a narrow opening and it will just reshape. This is how we make wire. You have a block of copper, you put it in a nice steel container that's sealed and you squish it through what amounts to a shower head. You don't actually have to get it molten, just a little bit hot and a massive amount of pressure and it will shove those atoms through the holes, but as long as they're still in contact, they'll hold together as one long chunk of wire. The third type is covalent. Covalent is bonding between specific atoms. And it is sharing of electrons. And so it's a little bit different. In ionic bonding, no electrons were shared. In fact, if you brought a sodium and a chlorine together, one of the electrons on sodium would just move over to the chlorine to make Na plus and Cl minus. They're not sharing electrons. They're attracted merely by charge. Metallic bonding is sharing electrons, but it's doing it in all directions. So no particular two atoms care about being next to each other as long as there's electrons in the way. Covalent absolutely cares which atom it is connected to. When I have a carbon to a hydrogen, and a hydrogen, and a hydrogen. So this is methane, CH4. That dash represents two electrons that are being shared between them. If I have a second methane, and you could mark all these atoms, you could mix this up, heat it, cool it, boil it, freeze it, liquefy it. When you came back, these atoms would still be together. And these atoms would still be together. But if you tried to do that with a salt crystal, melt it, dissolve it, cool it down, boil off the water, and reform the crystal, that would not be the case. Our sodium chloride, if one of these was green, we'll say one of the chlorides was yellow or red. There we go. If you were to heat it up, dissolve it, melt it, whatever, and then bring it back together later, those two that had been adjacent to each other have no reason to still be adjacent to each other later. Ions just care that any opposite charge is next to it. They don't care which particular atom. Covalents absolutely care which particular atom. This carbon and this hydrogen will still be together when we are done. Heating up, cooling down, liquefying, whatever it is we're doing to it. What is a covalent bond then? Well, it's an overlap, just like metals. I have some nuclei, I have some electrons, and both atoms are nuclei are attracted to both electrons. But unlike metal orbitals, which are large and diffuse, the covalent are much smaller. These tend to be non-metals, things in the upper right of the periodic table. Boron, carbon, nitrogen, oxygen, fluorine, chlorine, sulfur. As a result, they're a lot smaller, they don't have the reach and the range, they can't just interact with everything in all directions. And so they instead interact with just one thing with those electrons. The net effect of this is, well, I pull my atoms together. If they're originally quite far apart, the idea is that there's not a lot of attraction of the right proton to the left electron that's really far away. If I can get my atoms closer, then they can be more attracted. So I've moved my electrons on the same side. Let's spread them out here. The net effect is that I get my proton closer to the other electron. It's also getting closer to the other proton, and so it's a fight. On the one hand, you're being attracted to the negative, and you're being repelled by the positive. But the electron, because it's far out in its orbital, is a lot closer to the proton of the second atom. And as a result, there's, for a while at least, more attraction than there is repulsion. You can see this in a graph that basically says distance or radius r and energy. When we're far away, so when the atoms are very separated, we're pretty high in energy. As they start getting closer to each other, we start going down, and eventually when they're just the right distance, we're at the lowest. But then if they get too close, they start getting their nuclei too close together, and the energy goes back up. There's an ideal distance where you get the most attractive force with the least repulsive force, where it balances to the lowest possible energy. And so covalent bonds tend to have a bond length that's based on this balancing of those attractive and repulsive forces. What does covalent do besides share with a specific atom? Well, they have a large variety of properties. These tend to make very small molecules that are independent. As we said, these two methanes don't have anything to do with each other. If you throw more ions on an ionic compound, it just gets bigger. But if I throw more methane into a container of methane, I might have more methane, but each methane looks exactly the same. They're free-floating independent. And so these tend to make smaller molecules. They also are very common in organic. Because you can attach to one specific thing and it stays that way, you can construct large, elaborate shapes out of covalent bonds that you can't make out of ionic bonds. Ionic bonds just fill in as they keep finding more charges, but covalents you can build like Legos. You can piece them together in exactly the right order, and the same things can be put together in different orders to make different shapes. If you have sodium and chloride and you put them together, it's going to make one thing, but if I have carbons and hydrogens, how I put them together makes everything. It's the difference between methane versus cooking oil versus your cell wall versus the plants outside. They're all made of carbon, hydrogen, and oxygen, but they all look very different. And so organic molecules primarily use covalent bonds and get a huge amount of variety as a result. So these are our three basic forms of bonding that we're going to discuss. Here's a quick intro to those three.